Okay, I am here, Siddharth.
Okay, so then we can slowly start. So I think this is, so many people are already connected. So this is the last lecture of the academic or scientific session of this school. And I am very happy that Subhasis accepted our request to give a lecture on the future experiment CBM. And although there is no point or Subhasis introduction is not required to this audience, but just to follow the custom, I would like to request Supriyo to just formally introduce Subhasis and then we can start. Supriyo?
Yes, Siddharth. So Siddharth has given me a really difficult job of introducing Subhasis Chattopadhyay, who I am absolutely sure that does not need any introduction to at least this audience. However, as it has been given to me, I have to do something. So to introduce Subhasis, let me start with the fact that he completed his master's from the University of Calcutta and then joined the BARC training school and subsequently joined VECC as a scientific officer. And there he started his career in low energy nuclear physics experiment at the VECC cyclotron. And then slowly moved on to this newly founded research arena of this QGP field at that time by Professor Vikas Sinha and the experimental group by Professor Y.P. Vyogi. And then he did his PhD in WA93 experiment at CERN and with the photon measurement there. And then he continued and moved on to a postdoc position at Wayne State University in Detroit, Michigan, United States. Worked with the EM-Cal EM-Cal detector at the STAR experiment at the Relativistic Heavy Ion Collider. Came back to VECC, continued there in the STAR experiment and analysis for photon multiplicity detector. Then he joined the subsequent development was the ALICE experiment there. He also joined in ALICE experiment and took part in the development of the photon multiplicity detector for ALICE. Then he became, after Dr. Vyogi left this group after his superannuation, he started leading the group as the spokesperson of the ALICE India collaboration, continued there for 4 years. And currently he is the deputy spokesperson of the CBM Collaboration, which is going to be a new big experiment at the future facility of FAIR. And yeah, this was my kind of collection of information about Subhasis. And as I said, he does not need any introduction to at least this audience. I straight away invite him to start his lecture. Subhasis, please.
Thank you, Supriyo. Thank you, Siddharth. Thanks for this comprehensive introduction starting from my master's. Of course, I have been spending most of my life using nuclear physics. First with
Subhasis, I just said it from my mind. I don't have any note in front of me. Did I make any mistake?
No. I think you're right.
Thank you.
So it's 10 on 10. So no. Thank you, Supriyo. Anyway, so let me start this presentation today. I think you all have gone through this extensive and maybe sometimes long hours of lectures on ALICE experiment, data analysis, root, and of course physics of it. Now I will try to give you a flavor of some arena which is a little bit complementary to ALICE. I won't say it's different from ALICE. And that is what we have been trying to do for some time. And then the main purpose of my presentation, the way I thought that I will present the whole thing, is that as I understand today, whether it is STAR, whether it is ALICE, you are all, as a student, for example, you are in a situation which is not true, for example, Siddharth or Supriyo, when they started working for Alice or Star, because for you, the experiment is something like a black box to an extent, unless you are allowed to go inside, do something yourself. But as you know that it took at least on an average 10 to 20 years to build an experiment, and for which you are all now extracting exciting physics out of it. And there are several papers which are coming out. So what I will try to impress upon you is that the detector that you are using now, the data that you are using now, you are fighting with all the calibration, you are fighting with all the cuts. But then the journey to build such a detector itself is also extremely interesting and more challenging. So I will try to, because that is what we are all going through, some of us. So I will try to give you an impression that how difficult, or I would say how exciting that journey is also. So saying that, let me start my presentation. First, I share my slide and then I will go slowly over this. Okay, so I think it's seen, right, Siddharth?
Yes, yes, Subhasis.
Okay, so I will be talking basically under extreme density, the strongly interacting matter. As I said, it's an experimental journey. Now, this is like a cartoon. I think I'm sure many of you have seen, and this is shown as the kind of beginners or starting point. That what we do in our field of research. In our field of research, we try to create and characterize something which is shown with on the right as a soup of colored objects, red, green, blue, like that. And to create such a matter, which is known as Quark-Gluon matter or Quark-Gluon plasma, there are several ways to reach there. And because this is not the one which we see usually, it's not that we are in Quark-Gluon plasma phase. So we are said to be in Quark-Gluon plasma phase, like a microsecond old universe, but not today. So today, if we want to create it, we have to recreate the universe again, or otherwise we have to have some controlled thing which we will do in the lab. And in the lab that all of you are exploring essentially has two avenues. One is that which is schematically you can see like pictorially as an artist view is the middle one, which you are all looking at, that you pump up a lot of energy in a combination of, let's say, lead collisions. So you pump lead on lead or gold on gold, and then this energy will be converted to particles, which, let's say, in a lot of ions. And these created particles, maybe the original ones will go away, and in the middle there will be only energy, and that will create particles. And all those particles, the density will be so high that at some point of time you will not be able to recognize or distinguish from one point to the other, and you will create a soup which is shown on the right, and there is no boundary between one hadron to another, and they got when they were confined inside this, now they got deconfined. And of course, if you go into details, their masses might even be zero. So all those details, you know. Now there is another, this is what is called, usually called heating way of going to the Quark-Gluon plasma phase. And that has the similarity, or that is what is supposed to have happened in microsecondal universe. That is why it is called early universe. There is another way. Think of a nucleus, which, let's say, laid on laid, of course, falling one over the other. And the energy is not very high. That means you not pump up so much energy so that it creates a lot of ions. Of course, energy is not zero. You have to go inside this. But then, as it happens that when one collides over the other, then inside one nucleon, you might have many nucleons pushing together. If you have three, then it's three times. If you have four times. And then also what might happen that if you have a volume where there instead of one proton or one neutron, which is having three valence quarks, now you have many. And then the whole volume fills with such a dense system where the density is 3 to 4 times or even 6 times higher. And then also you will come back to a situation where all these colored objects, which are quarks and gluons, look free. And then also you create quark-gluon plasma. So that means there are two ways. One is at very high energy, which you do in Alice and the top star energy or top Rick energy. And the one which I am trying to emphasize today is the one which is compression. That means a relatively lower energy, so that when they collide, they do not pass each other. And then all the baryons to start with, they do not go away from the colliding zone, but they stop. And then when they stop, then you will get a baryon density, which is created, which is very high compared to the normal matter density, which is 0.15 per Fermi cube. And then you come with a situation which is look like a core of neutron star. And that also can be created as a Quark-Gluon plasma. So these are the two ways that you can reach there. I am sure all of you have seen this phase diagram once upon a time. This is how it used to look like when I started my career in this physics, in this field of research. It was so clean that it looks like that is the hadronic phase, which is shown here as white. And there is a Quark-Gluon plasma phase where all the colored objects are melted. And then, of course, there might be a mixed phase in between, which is between first and second order phase transition. And then there might be a critical point. But then this is what we knew about. And then in this field of research, as you know, that when you go to high temperature, which is on the y-axis, or if you talk about high density, which is on the x-axis, at zero density and high temperature, which is like RD universe, you go to a region of white to colored one, and that's the transition that you talk about. Now on the right side, there might be a similar transition because we essentially reach to a similar arena. But then it was not looked into that carefully. The way the field progresses, the way we started in 90s and then today, the things have happened that you only went up and up in energy. So you collide ions, of course, that was because you have to create a big volume. You collide ions and then you make accelerate, you go to one accelerator to another when you go from 1 GeV to 10 GeV to 200 GeV to 160 GeV, like that. So you pump up more and more energy. And it was said that, of course, if you pump up more and more energy, you will get Quark-Gluon plasma. That is what was the thought about. But I think after some time it was thought, no, this kind of rushing will not help. So let's sit down together and decide that how we will get Quark-Gluon plasma. Is it by increasing the energy only, or you have to have a dedicated experiments? And then the phase of dedicated experiments started coming. Like Rick, I believe, is the first experimental setup, like the high energy physics community do it, and Star, Phoenix, and Phobos and Brahms, they came up, and then followed by LHC experiments like in Alice, which is a dedicated one, which is having detectors which are dedicated for particular measurements, so that you don't miss anything when the collision happens. But that again, we're concentrating only on the high temperature zone. So we are only looking at pump up more and more energy, go to RIC or LHC, and then look at this. Now, if you look at the phase diagram today, this is how it looks like. Please look very carefully. This has changed. Look at that, how clean it was and how it looks today. You see that there are many things which have been added. Forget about the lattice QCD part, that's the theory part. But experimentally, there is a point which has been added with some error bar on the temperature axis, and there it's written perfect fluid. So this is an experimental point which has been added to the phase diagram, which you all know is said to be a crossover transition from hadronic phase to Quark-Gluon plasma phase, which many of you who are working in STAR and who are working in ALICE have already discussed about and talking, and in this school I'm sure it has been discussed about. Now if you go to the, now on the y-axis, you see the situation, it is very clean. But then there are many terms which have come now, like one is quark-ionic phase, which is like confined but maybe chirally symmetric. And there is, of course, neutron star, which you already talked about. It was said at the beginning. Then if you go to even higher density, you may get like colored superconductor where quarks will, it's like a Cooper pair which will be formed of quarks. And another thing is that there is another axis here. Instead of temperature and baryon density, there is another axis which is like neutron minus proton, asymmetry axis. And then you can make like a neutron star which is full of neutron and not proton. So you see now that the high dense, and of course the famous critical point, which is in between these two regions where there is a crossover, and maybe you will have a first order after that. So there has to be something which is in between, which is the critical point. So this landscape of our famous phase diagram has become very complicated now, and of course it becomes very colorful also. And that leads to a situation that, of course, you have got a fantastic results in RIC and LHC. You have got something which is a phase transition in the sense crossover, and you have put a point yourself. But then look at this region, look at very carefully. And then you see you will get a newer and newer physics, which is kind of exciting to all of us. And that lead to many other experimental facilities, namely RIC itself has gone down in its energy, which led to the beam energy scan facility. Then, of course, FAIR, which is coming up, and NICA MPD, and which I will talk about later. Now, before going into this, let's do a very simple calculation, which I'm sure all of you will be able to appreciate, is that if you take an atomic nucleus where you know the radius is R equal to R0 a to the power 1/3, and if you take R0 as 1.2, and if you take a volume as 4/3 pi R cube, then essentially what you get, and then you divide A, this mass by volume, then you get something like 0.14 per Fermi cube, which we call as the normal nuclear matter density. And then mass density is basically, if you talk about a mass, this is the number. If you talk about the mass, this is what is the unit that per centimeter square, take the number 270. So this is an atomic nucleus. So an atomic nucleus has a density which is 270 this ton per centimeter cube. Now you go to neutron star. Neutron star is an object which have been measured. The radius has been measured at least, which is about, let's say, 10 kilometer, and mass is 1.4 solar mass. So if you take these two and then volume as from the radius, you get the volume, and you get the density again, mass by volume, then you get it's like 2.6 times the nuclear matter density. So you had this value. Now you get 700, so you get essentially 2.6 times. Now this is what is the overall neutron star, which is shown here. But if you look into the core of it, all the models or all the theory calculation says that the core density is not just 2.6 times, because 2.6 times may be the surface, but in the core is much more denser, and then it comes out to be 5 to 10 times the nuclear matter density. Now, let's take a case of a gold nucleus, which is having the volume of 1400 Fermi cube, and number of nucleons, each one is about 2 Fermi cube. So that means in gold, we know it's 197. So for 200 nucleons, you will have about a volume of 400 Fermi cube. Now, the volume of a gold nucleus as measured is 1400 Fermi cube. Each nucleon is 2 Fermi cube. So 200 nucleons will take you 400 Fermi cube. So now if you go to 3 times of the volume, then it is 1200 Fermi cube. If you go to the 4 times of the volume, then it is 1600 Fermi cube. If you take even 5 times, then it is 2000 Fermi cube. So if that is what is the case, then this 1400 Fermi cube volume will essentially not be able to contain all the nucleons inside that. There has to be overlap in between them. So it's this simple calculation says that if you go to a nuclear density, which is 3 to 4 times the normal nuclear matter density, there will be an overlap. There will be a boundary overlap, and that overlap will lead to a situation where the colored objects will not know where from they have come, which essentially is the definition of Quark-Gluon plasma. Now, very recently, I'm sure all of you know about the discovery of the gravitational wave, and that gravitational wave was said to be, or first it was said that these are from the collision of black holes, and then there was a gravitational wave coupled with, or it was accompanied by photon signal, and they were supposed to be from the neutron star merger, as far as we know. Now, if two neutron stars, they merger, like the neutron star we talk about from the volume that we talked about, those neutron stars will essentially collide and will have a nuclear reaction at very high density, and that will lead to production of many kind of species, and that is said to be kind of light. So luminosity which has been plotted here, this is called kilonova. It's kind of simple light. It's not very bright light, but simple light that will create. Now, this is what was the calculation which was done in 2010, and this is what is the observation in 2017. And you see how well these two match. And so that essentially leads to a situation that neutron star merger will create elements, and for this nuclear reaction, you have to know what are the equation of state of these neutron stars. And to know the equation of state of the neutron star, you have to go to the lab and create neutron star. And that is what is done at lower energy that we talked about. So the similarity between this gravitational wave research that many of you know about by now, and the research that we talked about at high baryon density, which we'll be talking experimentally, is that we have to know the equation of state of the neutron star to model even this gravitational wave research. Now, neutron star mass, if you plot, it comes out up to the 2 times or 2.5 times the solar mass, and that cannot be explained without having a core which is made of quarks and gluons, and that region is said to be from 3 to 5 times the nuclear matter density. So if you reach 3 to 5 times the nuclear matter density, you will go to a region where there will be quark-gluon, quark matter inside the core of the neutron star. Now, there have been, of course, serious calculations on the neutron star merger, and this is the time when the merger happens from 2 millisecond to 15 millisecond, and this is what is the quark content inside this, and this is what shows the temperature on the y-axis. So this is like, it's a hot region. It's not completely cold like a neutron star. It's a hot, relatively hot. And this is you see white like, it's like almost full of quark. So it's a quark matter which is there inside, and these are the contours of different densities, and these are the 3 times density. This is the phase transition in the relativistic neutron star merger. When 2 neutron stars get merged from 2 millisecond to 15 millisecond, you create a region inside the core, which is the quark-gluon plasma region, or the quark-dominated region. So there is a transition at rho greater than 430 and temperature 500 MeV. Now, the similar calculations have been done in heavy ion collisions, which is, let's say, 1.5 GeV. And as you can see, this is the same axis, temperature and density. And you see there is a region inside which essentially looks like a neutron star. So the statement what I'm trying to make here is that if you go to heavy ion collisions, you can essentially create a situation which is like a neutron star merger. And that certainly is a fantastic tool to understand something which is gravitational wave and neutron star merger. So we need to know the equation of state so that you understand the thermodynamics of both the objects. Now, before I go into the experimental part, this is the talk, this is the slide which I got from Jan Poloski. He showed these slides in the October CBM collaboration meeting. And there are 2 plots. One is on the y-axis, it's the center of mass energy. And on the, in the x-axis, center of mass energy. And the y-axis, there is an interaction rate. Now see, this is star at Rick. This may be Alice. And see the interaction rate, like 10 to the power 4 collisions per second. So it's 10 kilohertz. That's the rate that we talk about. And all others like star fixed target, NS61 sign, and all others are like 10 kilohertz rate. And this is the energy that is going up. But there is a shaded region here, as you can see, which will be covered by, it's a new critical endpoint and other new physics or phases. Here you see there are facilities which either are coming up or existing, like HADES is existing at GSI. There is a facility which is coming up called CBM, which I will discuss in detail, will run at 10 to the power 7 collisions per second. So that means 10 megahertz interaction rate, which as you compared with 10 kilohertz interaction rate. So whoever is having a little bit idea about the hardware and taking the pictures with a camera, think about that earlier you were taking 10,000 pictures per second, now you are taking 10 million pictures per second. So that is a completely different change in the technology and all other. But interestingly, that is the region which is again shown in this shaded region where the density is very high, and that is the region which will give us an interesting physics. And that is what we are discussing about. And I am trying to give a motivation that why we need to go to lower energy to do this. Now, these are an interesting slide which is shown in CBM collaboration meeting. This is temperature and this is chemical potential, which is connected to density. And as it says, this location of critical point, there have been several theoretical models and theoretical calculations where the models and the calculations, they predict that where the critical point would be. That means where this second order will become first order, and that's the junction that we need to know about. Now you see the number of, these are the papers which you can all look at. And these are the locations where the critical point could be. It starts from like 800 MeV here, which is a very high density, to even 200 MeV, which is like RIC or LHC region even. So these are the uncertainties theoretically in giving the location of the critical point, which we are all looking at. Now see the problem here at high density, unlike high temperature. In high temperature, where the net baryon density is 0, you don't have any net baryon. That means baryon minus antibaryon is equal to 0. It's called pure Quark-Gluon plasma, or pure gluonic system. And that can be calculated by lattice QCD exactly. And then when you talk about the phase transition, crossover, and all other, all those conclusions have been drawn using that lattice QCD as the background. That means you have taken, it was all inspired by lattice QCD. It's not the number has come directly from experiment. You compare with lattice QCD. That means you believe lattice QCD there. But the problem at high density is that because of some technical reasons, which they call a sign problem, this calculation cannot be done. And when this cannot be done, people come up with models like a PNGL model, NGL model, and those models are basically close to the lattice QCD. At some point of time, matches lattice QCD or doesn't, and then they give the prediction. And that prediction tells you, form an experiment where the critical point is here, which is a very high density, you will get a critical point. Or they tell, form another experiment here where critical point might be here. It is something like the deer that we are all looking everywhere. We do not know where it is. Somebody has told it might be here. Somebody has told it might be here. Somebody has told it might be here. And this is what is the compilation, which was from 2004 to 2020 calculation. But interestingly, in this talk, Jan did a very fantastic thing. What he did, first to remove all the points which are old critical endpoints calculation, which are based on lattice or the functional QCD approaches. And he said for all of them, updated computations are available. So they are old, just forget them. So he removed them. Then he removed the ones which are again qualitative approximations, and they do not match at mu b equal to 0. So that means you are doing calculation at higher mu b, but they do not match your lattice calculation and may be equal to 0. So how they cannot, there is a problem here. So remove them. Then finally, he removed that missing Quark-Gluon back reaction in all these calculations. And you see which ones remain now? Here, these two. These two only remain, and they say that this is where the critical endpoint might be. The theoretical calculations, which are all believed to be, means which you can rely on to an extent. So essentially, the point which I am trying to make here is that it's very difficult to form an experiment. So you have to have an experiment over the whole region and see if you get a critical endpoint somewhere. That's what the community has been doing. It started in 1984 with the Bevalac, which is at Berkeley, which is having less than 2 GeV as the lab energy. And these are the detectors and projectiles that were used, followed by at Brookhaven lab, alternating gradient synchrotron, which was upgraded later to RIC, 1986 to 1994. Then superproton synchrotron at CERN, 1986 to 2002. You see the energy is increasing, 2 GeV, 14 GeV, 200 GeV. This is a lab. So then there is another one in between, which is GSI Darmstadt, which is a fair site now. It is still running, which is again at 2A GeV. So they are consistently doing lower energy. And then suddenly there is a jump at RIC at Brookhaven, which is also still running. Highest energy is 200 GeV. And then, of course, we have done the beam energy scan. And then came LHC, which has started giving you results at 5.5 TeV. And then now, interestingly, you come back to the lower energy again. From 1984, 2007, you are just pumping up energy, and you come back in 2025, maybe now also through beam energy scan, that you look at the lower energy, 11 AGV, 15 AGV, and there are two facilities which are at, one is GSI Darmstadt, another is GNR Dubna, one is called Nika, another is called FAIR, which is coming up. You all know that when the collision happens, you have particles which come out from all the phases, and depending on the particles and their characteristic, you can understand every phase. And this is true all for CBM or FAIR, CBM or STAR or ALICE, because these are the normal properties of heavy ion collision experiments. Now, beam energy scan we have talked about. I'm sure many of you have been working in analyzing the data from beam energy scan. It's a fantastic, fantastic kind of effort or step taken by the STAR collaboration, where they have changed the energy, let's say from 200 GeV, which is the highest energy, to you go lower. Even there is something like at 3 GeV somewhere in between, which point is not here, shown here. Which is the fixed target. That means you have beam and it hits the fixed target, and the center of mass energy, of course, will be lower then, and then you get a root S of 3 GeV. Before that, there was 7 GeV, 19 GeV, 15 GeV, and all others. And what has been plotted here is the fluctuation of the conserved quantities, which is, I believe, proton, antiproton. And you see that this fluctuating quantity, which is a robust quantity, and that fluctuation goes down and then it starts going up. So there is certainly beyond this 3 sigma level signal, where it shows that there is a which cannot be explained by URKMD or AMPT or any other transport model. And so there is something happening here because of this non-monotone shift. But the one which interested me very recently is again this 3 GeV. Many of you know that this V2, this is V2 by NQ. That is what is plotted here. Sorry for this bad slide because it's got chopped up. What is shown is VT by NQ versus MT minus M0. Now, as you can see that there are different energies, 200 GeV to 7.7 GeV, and almost they are falling one over the other when you divide them by number of constituent quarks. And that is what is called constituent quark scaling. And the conclusion which was made is that the flow or V2 that you get are from quark level. That is why when you divide by the number of quarks, then they all kind of show similar values, and both for positive and negative particles. But you see, interesting what happens at 3 GeV, and this is where it is. There is absolutely no match whatsoever. And so what happened? Have you completely changed from a phase which might have been quark dominated phase to a hadronic phase? So then there must be a first order phase transition somewhere. So critical point might be somewhere from 3 GeV to this. This is certainly interesting, and I am sure STAR is also looking at it. Now I go to a facility. Which is called FAIR. I'm sorry if there is a background noise because all the kids are playing a lot. They have found some chance now to play. I hope you can hear me. Now, this is a facility which is called Facility for Antiproton and Ion Research. And India is the third largest contributor in building this accelerator facility, where many of us, including Bose Institute is the main institute who are spearheading all the efforts. Now, this facility, I would like to mention some of the prominent features of this facility. This is called existing GSI. This GSI is existing for several decades by now. It's a nuclear physics facility. And this has discovered 7 periodic table elements, including one called Darmstadtium, from the name of Darmstadt, where it is situated. And then there is a Hessium. The name of state is Hessen, so it's called Hessium. And then there are, of course, like Europium and all others. This has been discovered. Now then they decided to make it an international facility, and then all these colored accelerator complexes, they are coming up now, and whole thing is called FAIR. So this is the main ring. So beam is coming from here. It's a boost injector, and then it got accelerated here. There will be two rings. One is cis100 and cis300, depending on the rigidity, and that decides the energy. And then there will be a switching hall. That switching hall will give beam for 4 different kinds of fields of research. One is compressed baryonic matter, which is our field of research. They will get beam first. Then, of course, it's a nuclear physics facility, so there will be a production target, and that target, the beam will hit the target. It will create all the rare ion beams, including radioactive ones, and they will all be used for nuclear physics experiment later. And then, of course, there will be antiproton, which will be used here for proton antiproton for the hadronic structure reaction, and then atomic physics and plasma. So this is a facility not only just for our like CERN, it's a particle physics one, it's a high energy physics, nuclear physics, atomic physics, plasma physics, and of course applications of this. It is having high intensity beams. Energy is not very high. Energy, proton energy maximum is 90 GeV in the final phase. In the initial phase, 30 GeV, and heavy ions will be like up to 12 GeV in the cis100 region. It's a high beam intensity, which is the main feature here. As I said already, that the physics program of FAIR will have a high energy physics region, which is almost at the microsecond level universe. There will be nuclear physics region, which creates the nucleus, and then of course atomic physics, which you all know, and space research. Let's take a pause here. This is a fixed target experiment. This is not a collider, unlike STAR or ALICE. In STAR and ALICE, you have seen this, that it collides at a point, and then there is a barrel region, all the detectors are around it, and then there are end cap regions, like PMD is one of them, muon is one of them. Here it is a fixed target experiment. So the beam comes from left, and this is the hardest experiment, which will also be in the same hall. So it is shown there, but let's concentrate on the CBM part of it. So then this is a magnet, dipole magnet. There will be a target inside it, and there will be silicon station, 8 of them inside this for doing the tracking inside a magnet, which will give you the momentum of the tracks. This will be followed by 2 phases. Either one of them is ring imaging Cherenkov counter, which is for the electron identification, or muon chambers, which is for the muon identification. So think about it, that all the particles will be produced, charged particle will be tracked here, but then it will detect dilepton, that means dimuon or dielectron, either in one dimuon mode or in dielectron mode. Why dielectron and dimuon? Because these are the ones which are produced at the very beginning. And when they are produced at the very beginning, you all know by now that they carry because many of you are analyzing the heavy flavor data, photon data, they all come from the beginning almost. So these are the ones, and the strange particles, multi-strange ones, they all come at the beginning when you have good amount of energy to create those, like pions and pion, kaon, proton, and lambda. So this is important, that we detect the dielectron or dimuon, which essentially is decay product of the particles which are created at the beginning, and which might get modified inside the zone, the reaction zone. And another very important point is that I will come back to this later. I just want to show this, that you see here, that if you talk about GEPSI, many of you are analyzing ALICE data for GEPSI. And I don't even care if you have a million events, you have a large number of GEPSIs which are produced. But if you talk about GEPSI in CBM, even at highest energy, which is 25 AGV, it will be 12 AGV to start with. You see the number of GEPSIs which are produced per collision, 10 to the power -7. So that means you have to have 10 million collisions to get one GEPSI. So to have a reasonable statistics, you have to have billion collisions in reasonable time to do any physics from GEPSI. Forget about epsilon if you have enough energy. So given this, all this situation, what is required is that either you give enough time, years after years, or you increase the intensity. So that is what is done in CBM, that you increase the intensity and do the experiments. Now, what has happened because of the increase in intensity? What are the problems that you face? Now I take you to the, as I said at the beginning, building an experiment. So you think about it, that you do simulation and you have to have up to 10 to the power 7 collisions per second, which will create a huge particle rate. You have to, of course, know all the particles. So you have to have displaced vertices where the resolution should be 50 micron. Detector. You have hadrons. You have to have fast and radiation hard detectors because this is a huge intensity experiment. You do not have enough time. You do know in ALICE, when you do an analysis, somebody tells you that are you analyzing central data? Are you analyzing high PT data? Are you analyzing EMCAL triggered data? And I'm sure you all know what this trigger means. That means you collect only those collisions which are having some signature which shows that it might be a central collision, or it might have a photon inside, or it might have a JEPSA inside. But in CBM, the number of particles, interesting particles produced are so less, like 1 in 10 to the power 7, you don't allow it to have any selection. This is number one. Another thing is that if you allow a selection, selection is also done by a set of detectors. This will also take its own time. So even if you take 1 second, you essentially lose 1 million collisions. If you take 1 microsecond, maybe you lose some order of magnitude of interactions being recorded. So you don't have any option to do any trigger. What you do, you collect whatever comes and do the analysis later. And that's called free streaming readout. That means it's coming. You don't hinder it. You just don't stop it. It keeps coming. And that essentially leads to high-speed data acquisition and high-performance computing. And then you have to have 4-dimensional reconstruction. Let me introduce the term 4D. You all, whoever are working on TPC, you know TPC, the points are 3D. That means you have X, Y, and Z. XY comes from your MWPC or from GEM, and time will come from the transit time of these tracks to reach the MWPC or the TPC detectors. That's 3D. But here, we have to have, because we do not know which collision we have recorded. There may be mixing of all the collisions together because I collect all of them. So I have to separate them. So every signal that we collect, we will have X, Y, Z and the time when it happens. So that later on we can club them using the time. And we have in India the whole muon system, which if you look at the ALICE dimuon absorber, which absorbs all the other particles like pions and others, and there are detectors after that. That is what is ALICE. If you do something in CBM, the energy is low, 12 GeV total, which is much lower than in ALICE. So muons will also get absorbed. So the philosophy that has been taken is that you will keep putting absorbers of different thicknesses. This is called segmented absorbers, and then put detectors in between. They will give signal in between. And then you see if the guy comes up to the end, then it might be muon. If the guy comes up to there, then it might be a pion, and then you just throw them away. So that means you end up with building so many absorbers, end up with building so many detector stations in between. This is what we are all doing. And the detectors that we are working, many of you might have heard, I do not know if it has been told or taught in the school, is called GEM detector, gas electron multiplier. This is to an extent the most advanced gaseous detector now, which can give you resolution up to 300 to 500 micrometer. And of course, good time resolution. And most importantly, it can handle high particle rate. Because again, I am saying, Alice was working in 10 kilohertz. Now we are working in 10 megahertz. So detectors should not be such that you cannot process one collisions after the another. So your detector has to handle that rate. So the rate we are talking about is like a megahertz per centimeter square, and GEM detector, the way it is built to handle such a rate. So these are the GEM detectors which are being built, here, and this is one chamber which we have already built and tested in a accelerator facility called COSY, Cooler Synchrotron in Germany, in Ulis. And then the beam hall was called Jessica. So that is where we first tested, and that is proton beam, and that is done in 2014. So think about when we started the journey of building an experiment, which is called CBM, and a sub-detector called muon chambers. So we built the detectors, tested them, got some results. Of course, you won't have to go into details. Most important is that you get efficiency up to 95%. Your gain increases with high voltage, and efficiency remains stable up to 3 megahertz. So that means the GEM detector can handle high rate up to 3 megahertz, which is beyond what we need. But then that is what is only proton beam. But actually the detector will be used with heavy ion collisions. That means gold on gold. So we must test our detector at that rate in heavy ion collision environment. And that is what is being done in the last 3 years. A setup called mini CBM or MCBM, which is basically all CBM detectors inside. As you can see, this starts with silicon detector, MSTS, mini silicon tracking station, which is inside the magnet as I shown. Then mini match. So there are two GEM station here. It is called mini match. Then mini transition radiation detector, then mini time of flight detector, and mini ring imaging Cherenkov counter. So that means this is a facility where all the detectors which will be used ultimately in CBM in full glory are being used to take data for two reasons. One is that the data acquisition system, which itself is challenging to take this megahertz of interaction rate, will be exactly same as will be used in CBM. And you can test your computing farm, and of course you can test all your electronics. And the data which has been taken is from GSI facility CIS-18, which is argon plus gold, and of course later on we take lead on lead also with 1.7 AGV, and then the beam intensity went up to 10 to the power 8 per spill, and target thickness varied. Now this is what is life. We took data in 2019. We installed our detector, took some interesting results, and got a nice time correlation, got a nice spatial correlation, and we saw that when there is a beam on, which is called spill on, we have our hits on our detector. When there is spill off, that the beam is not there, we don't get it. So this is nice spill structure which you see. So the detector works fine, at least in the 2019 and part of 2020. And then in 2020, of course, it came Corona. And what the picture which you see is the remote data taking. So all the detectors were handled remotely, namely high voltage, low voltage, gas, temperature, and all were controlled remotely. And some of our collaborators from India, which is Soda Star, which is Vikas, Shreya, Apar, Anand, and here Chandrasekhar, which are taking in the midnight shift, because that is when the data were being taken. And these are two of our detectors which took data in the mini CBM. And of course, Bose Institute built a special kind of object based on aluminium, led by Siddharth and all others, which is for cooling the whole electronics, because that will generate a lot of heat. This is what is the electronics part. This is called green cube, which is built in GSI, which will have a power dissipation at least an order of magnitude lower than anywhere else. And then the data which will come from the front-end electronics to something called serializer, and then it will go to data processing board, and ultimately it will go to this green cube, and where you will analyze. So this is more of an computing experiment than, because it's a petabytes of data that we are talking about. So 1 terabytes per second, and then ultimately it will be petabyte. These are the results, some of which I have already shown, so I don't want to spend on this. And these are the results when we compare with other detectors. That means, let's say this is between two, T0 and GEM, which is a nicely correlated number of hits. This is GEM1 and T0, GEM2 and T0. This is between two GEMs. This is between time of this is between T0 and another GEM. So you can see that one detector is saturating, which is T0. So there is a problem with T0, not with GEM, because GEM essentially is linear with other detectors. So you see, yeah, it's working fine, which is basically low intensity at high intensity. And we have a spatial correlation between two gems. That means if the particle hits in one place, the X position will have another place, and then you will see particles looking nicely as correlated in X and Y. And we studied how much intensity we got. It is only up to 25 kilohertz. That is the maximum that we got. But where we'll run, we'll need to run at least per centimeter square, it has to be 400 kilohertz per centimeter square. So we are far away from that. But then we see that with different intensity, of course, it's linear, but then there is a problem here. We tested the detector even up to 1.3 megahertz at CERN with X-ray source, and then the ADC value remains stable. It doesn't shift and it doesn't go down. So detector works fine even at higher intensity. But then in this experiment, that means mini CBM, we have faced a different kind of problem. If you go to high intensity and high voltage, then the connection link between the detectors and the data acquisition get lost. That we call as link loss. And this starts happening more and more at high voltage and at high intensity. So in 2020, we had to stop taking data, and 21, we could not take any data, first because of pandemic, and second because unless we solve this problem, because detector is not starting at high intensity because there is a problem. This is what is called link loss problem. We worked in the lab for last 1.5 years, and then the solution that we have come up, this is what is the electronics where high voltage is used using a device called optocouplers. Optocoupler is something where the high voltage can be disentangled from the main chamber. If there is a spark, then you use the optocoupler and then the high voltage will not go there. And they are all connected through 1 megohm resistors through the optocoupler. And this seems to be the problem. So now there is a change in the configuration in the high voltage. It's not one line that is connected. This is modification as compared to the earlier test. And only last week, we have taken test beam at CERN. Many of the colleagues are at CERN now, and they have taken data with RPC, because that is another set of detectors that we are building, including Bose Institute. They have a lot of activities of RPC and GEM, and we will have a high intensity run in February, March. And once we are successful with high intensity run, then only we can start working on production of these chambers. So still there are way to go, even though we have started a long time back. Now there is another way of the mechanical part. It's like 100 ton absorbers. And when muon will take data, this is the data taking position. When muon will take data, electron reach will go away. But when electron will take data, we have to move it to a called parking position, where you see this is stretched one. And this is what is the cable carrier. So you see what is happening. The cables are going from down, and then it goes up as soon as you compress them. And this all comes from up. And this is the huge thing which you can see from here. These are detector chambers. So the cable comes from, so from first one, the cable carrier. And then in the second one, it goes through the cable carrier, goes down, and then ultimately it reaches through this to your detectors. So this is a huge setup which you are all working for the mechanical design at this point of time. This is how our detector will look like for the first station. There are 4 stations like that. So this is how it will look like in the first station. This is the gas system, because these are all gas detectors. And this is a closed cycle loop. That means the gas will be used. And again, the mixed gas, and if there is a contamination, it will be cleaned and then used again. It's a closed loop gas system which will be used. And now I come to my almost last slides, where we are so far as the accelerator is concerned. As I have said, this is GSI. This is the picture taken from top, from helicopter. And this is where the main ring, this is FAIR, and this is GSI. This was before July 2017. In July 2017, the civil construction started. And this is the huge tunnel, which is a 60 meter wide and 20 meter deep. And now the tunnel is ready. And the car is essentially going over that. And you can move from one place to other, 1.1 kilometer. You can have a morning walk if you want. And this, all the other experimental halls and others are being built now. And which is most CBM, you see you heat it, and all the experiment, all the detectors will sit here. There is no roof here when the picture was taken, but I have been told the roof is already in place now. So this is my last slide. I have tried to impress upon you that over the years or over the decades, the strongly interacting matter under extreme conditions, initially it started by increasing the energy, which essentially takes you towards the high temperature phase. And that essentially has given you a new set of results or a fantastic results at RIC and LHC. And now, because of the theoretical works and the structures or the new phases that we are talking about in high density region, there are renewed interest in the high density region, which is at lower energy. And worldwide, several experimental programs. I only talked about CBM and briefly about beam energy scan at STAR. There is a program which is coming in Japan, which is at JPark. There is a program, of course, which is coming in Dubna, Russia, which is called NICA. That's a collider at lower energy. And activities in CBM is picking up. As you can see that we have started working for CBM around 2007, where we built our first 10 centimeter by 10 centimeter gem chamber. We could build now any number of gem chambers of 1.2 meter by 40 centimeter, but still we are not out of the woods because we are still working how to run it at high intensity. Maybe we have already solved the problem because at CERN test beam, even at high intensity, it did not show that link loss problem. So let's hope that this works and we'll then start producing. And I'm sure many of you will join these activities very soon. Thank you very much.
Okay, thank you, Subhasis very much for this nice discussion about the physics at net-baryon, high net-baryon density, the technicalities of the CBM experiment and the current status. So now we are open for questions. So you can raise your hand or you can directly speak after unmuting yourself. Please raise your hands if you have questions. So there is a comments from Ramani ma'am. So in the chat box, she writes, thanks for quite informative talk.
Thank you, Ramani.
There is one hand raised. Upper, can you please ask, unmute and ask?
Yes, thank you for the talk, sir. I was interested in the free streaming data which you talked in your slide. So how is it different from the one we have taken Alice? Once you told that it is triggerless, one point is that I was interested in how it will be taken and analyzed in the CBM experiment.
Yeah, very good question, Apar. In Alice, when you say that I have a trigger, that means you have the data taken for every collision. Your online hardware has decided that this is the beginning of a collision, this is the end of a collision, unless there are, of course, pileups, which happens at high luminosity. But otherwise, it's a clean collision, and you have all the particles which are produced inside these collisions, and you analyze them without thinking that if there is any other collision coming here, because the physics has to be a complete collision and physics has to be only one collision. You cannot do physics by two collisions putting together or half of a collision and 75% of the collision. So in Alice or the experiments, which essentially works in the trigger mode, they make sure by many means that there is only one collision and that's the full collision. That's the called trigger one. Now here the problem, as I said, because of different reason, we take all data. We don't care whether it is coming from collision number 1 or collision number 10. We put them, and only additional information that we give is that for every signal that we collect, we assign a timestamp to that when this happens, which of course with respect to reference. Now, for example, that there are 10 particles or 10 hits, 10 signals, which are coming within a few nanosecond time interval. And then the interaction rate that you know is of the order of, let's say, 10 to the power 7, which will give you 10 to the power minus 7 per collisions. So that means in nanosecond interval, they cannot be from two different collisions. They have to be from the same collisions. So the way it is done is, now you take those timestamps, club them together, and make bunches of them, that these are the ones which are very close, and of course reasonably close, not that you put a time window of 1 second and tell this is my one event. And then you assign all those particles as from one event. This is one way of doing. Another way of doing is that don't do event reconstruction at the beginning from the heat level. Whatever heat you have, if they are time correlated, you just make a track out of it. So it's a charged particle which are going through it, you know the momentum of the track, and then you see where from they have come. And then from vertex or somewhere else, you just club together like it is done in Alice, for example. And then you say this is one event. And there the problem is that you have to do 4D tracking. That means you have to take the time also, not only XYZ to make the track, but time also. So this is how the philosophy which will be used.
Okay, thank you, sir.
Okay, then we have one more question in the chat box. This is from Rudrapriya, I think, Bose Institute. Sir, what is kilonova? How it is differ from supernova? Sorry, my mic is not working. Okay. So Subhasis, you got...
You see, this kilonova or supernova is basically burst of light. That's what this name came. Now, this kilonova is like, I think it's a German term. I have to check where it is, the exact origin. But essentially, it's a small light. So what happens is that when supernova is in some sense is a big light, in the sense big collisions happen and then you generate a lot of light. But these lights are basically creation of elements. Those elements, when the collision happens and the elements are created, as you know, all the golds that you use are produced by supernova collision or some collisions, maybe neutron star or whatever. So if these elements are formed in the excited state, they will generate light. And those lights are called kilonova. And that is what is the term which I think coined by them only first, is that it's not in that sense the light which comes along with the gravitational wave from neutron star, but these are the small lights which come from the elements which are created from these collisions.
Okay, I don't see any more questions. So maybe, may I ask a question?
So there is one from Sapnesh, I see that.
Yeah, so Swapnesh, you go ahead and then maybe I can ask later on.
Yes, sir. Thank you for talk, sir. So I'm interested in this neutron star equation of state kind of study.
Right.
As you mentioned that in CBM we will be targeting the study of equation of state for the neutron star at high baryon densities. So what are the data which we will get from the neutron star, it is mainly will be photons, right? I mean, not the photons, I'm saying. The photon is the main messenger from the...
No.
Neutrinos are also there and gravitational waves are also there, as you mentioned. But
you are asking about the models or you are asking about experiment?
No, I'm asking since photon is the only messenger which we are going to...
Oh, acha, that's your question. No. So
yeah.
the difference is that, you see, as I said, that gravitational waves could be produced by the collision of black holes. Yes. So the first gravitational wave which was detected, and people Boris got Nobel Prize, that there was no photon associated to that. So what happens later, some later events, all the gravitational wave detectors detected gravitational waves. At the same time, there are some other detectors over the world which were not for gravitational wave. They were to detect some radio wave or some waves of some frequency, which you call light. And so they also simultaneously saw the light or photons. So now the origin of this it was predicted earlier, not that it came after it was observed, that this kind of collisions must come from the collision of neutron star and not from black holes. So that is where this neutron star collision came and gravitational wave came. Now the equation of state in CBM we are not, of course, not colliding two neutron stars. CBM, what we are essentially doing is that we are creating a density which is equivalent to the core of the neutron star density. Now the particles which are coming out of the CBM, like we are doing an Alice and star event, because they are high temperature, it's a thermodynamic system. So in the thermodynamic system, all the variables that you have, like flow and particle multiplicity and all others, that will all be used to get the equation of state. And that equation of state can be now fit in the models which are trying to explain the gravitational waves. So this is how they are connected.
Sir, in your lecture, I had one more point.
Yes,
I missed you mentioned there are 2017 data points, those red data points. One of the plot, the nuclei produced in neutron star merger. I think that kind of plot was there, that there was a prediction from 2010 data and 2010 and some red data points from 2017 observations.
Yeah. Those are
So
kilonova ones. Those are kilonova.
so I just wanted to know that the line which was fitted, I mean, which was predicted, what was the basis? Equation of state is not there for us, right? I mean, to calculate that particular.
It was basically, this equation of state at high density is a matter of intense investigation among the nuclear physicists for long. Not that we are doing it for the first time. So there are many equations of state, and high density, it becomes more complicated always. Because it's it becomes hard or mix or whatever. So in GSI, in nuclear physics, they had a lot of, there is something called FOPI collaboration and other collaborations. There is in fact one equation of state collaboration, if I remember. So they had some equation of state which was measured at the known energy. But then they extrapolated using the model that what will happen at high density. And that is what they have used here. So in that sense, it was a prediction. It was not matching data. Data came later. And then it was, interestingly or nicely, that the data is also close to the line. That's all the statement that I wanted to make. Okay, sir. Thank you.
Okay, there is one more question, Subhasis, by Priyanshi Sinha. I guess I said Tirupati. Sir, what is the advantage/reason of using anti-proton beam?
Oh, okay. So actually, we will not be using anti-proton for CBM. Anti-proton is used for different reasons. In fact, getting anti-proton beam is very difficult, honestly. But this will be used for an experiment which is called PANDA. PANDA is full form is proton anti-proton at Darmstadt, something like that. Now, their main goal, it's like LHCb kind of experiment. Their main goal is to understand the hadronic structure. Hadronic structure means QCD, basically. Like yesterday, you might have heard the talk of EIC. So it's similar, but what they will do, they will essentially collide. This is a fixed target, it's not collision. So anti-proton beam will hit the proton, and then it will create energy, basically, and then that will create resonances. So those resonances they will study to understand that what was there inside the structure of proton. Now your question about why anti-proton? They could have done proton plus proton, but you know that when proton and anti-proton collide, they annihilate, and they annihilate means you get 2 GeV energy basically free. So whatever beam energy you have in addition to 2 GeV, and that essentially adds to your total energy. That is one option. Another option is that in case of proton, there are a lot of debris. But here, if it annihilates completely, you only have energy. And then you have resonances which are coming out of it are all clean. That is why people have used anti-proton. Anti-proton is not for CBM physics, but for PANDA physics. Okay.
So yeah, okay. See, heard it. So one more question, Swashisda, from Ramani Gupta, Ramani ma'am. Theoretically, it is predicted that there is crossover from hadrons to quarks at LSC. What is the best signature for that? Experimental signature.
But crossover, I think people, whoever, I don't think there is any smoking gun signature as such that it says that this is the crossover. Like first order, that there is a means caloric carb or temperature goes up. Temperature, you have a kind of melting point or whatever, latent heat kind of thing. But in crossover, you know, all the signals that you get are not of the hadronic medium. They are all partonic medium. So if there is a partonic medium which is formed and you started with an hadronic medium, then how did you go there from hadronic to partonic? So that's the question. And there came the lattice calculation. So lattice calculation with mu b equal to 0 at that energy at Reek LHC, they say it has to be a crossover transition. And at a temperature of around 155 plus minus some number there that we talk about. And that is where it comes. So as such, crossover is something, as you know, that when you don't have first order, when you don't have second order, then you have something like evaporating something. It's changing the phase, but it's not sharp. It's a continuous in that sense.
Okay, then so what is the last, maybe just I should ask one small question in the end. So we have seen the challenges in building the detectors at CBM because of the high luminosity and high rate. So what are the kind of challenges foreseen for the physics analysis?
Yeah.
So Vasudha, your voice is choppy. So
and so say what is called 4D tracking in the environments. So event reconstruction itself is a challenge, which is not a, in that sense, not a physics analysis, because if you can do your event reconstruction well, then comes the physics. Now here the physics, the way I understand, as the rate of production is extremely low, as I said, 10 to the minus 7 for Quark-Gluon. So here the background will be very high. So get anything which is signal from the, means this is what is the, means people suddenly is asking that if beam energy scan has already shown something, why, what is new in CBM? Now, of course, the uniqueness of CBM is, of course, the high intensity and high interaction rate. Why high interaction rate? That's for a reason. Because this will essentially capture all the sub-threshold particles which are produced, which are not supposed to be produced in normal collisions, or the particles which are having rate of 10 to the minus 7. So the question what I am saying, when you will do analysis, when you will have all the events in front of you, when you will have all the tracks in front of you, and you will write a code to find out, you will certainly face problems in background. And that removal of background, physics background and other background, I think in my opinion would be the main problem. Because right now we are talking about signal to background, for example, in rho and omega kind of the level of 10 to the power minus 4 sometime. So you know what that means.
Siddharth, I will add to what Swasida said. There may be two other things. One is PID acceptance, right? Swasida, PID acceptance.
Yeah, for a collider and a fixed target. Yeah, that's true. In fact, I wanted to add that slide. I forgot that later on. That's a very good, important point, Vedang. PID acceptance in fixed target and collider experiments are completely different. In fixed target, it's a uniform one, means around 0. No, sorry, in collider, in fixed target, essentially it's forward focused. So that's a different, and that would be a problem, because if you, for example, want to do something at mid rapidity physics, and in a collider you have equally, your cylinder will give you acceptance on both sides equally, but in this case your mid rapidity, maybe your detector which are away will give you on the left side, not on the right side. So that's certainly a problem. That certainly will be, but it depends on the energy. This is another interesting thing I'm telling you, which you have felt in CBM. You see, if you, because the plan is to run from 4A GeV to till 12A GeV. Now see, at 4A GeV, the beam rigidity, you have a magnet, dipole magnet. So it will happen, the beam itself will move by this magnet. And so beam will not be confined inside your beam pipe, and it will try to come out. So what we are now discussing, that how to make a beam pipe which essentially will move. when you change your magnetic thing. So that's the problem when you go to lower energy. So because lower energy, that is why people have not done too much of lower energy. It's not only physics part. I think higher energy experiments are much cleaner and easier because the higher momentum particles are all away. So that's certainly a challenge. Sure, good point, Vedant.
Subhasis, the one more point. This is fixed target. How vertex finding will it be easy like primary vertex?
Yeah, it depends on the thickness of the target. If it is a very thick target, you will be in trouble because the vertex where interaction happens, it might re-interact again before it comes out to your detector. So that is why one cannot use very thick target. So you have to use thin target, and people use segmented target also. So that means like for example, Na49, I think they used. So you will have a target wheel. So and they are very thin. So interaction, if it doesn't happen in the first one, will happen in the second one. But then the vertexing will essentially be in the back. Means like the way we do, the track goes back and then you take the vertex. And of course, we will have a vertex detector also as well.
Okay, thank you, Subhasis. Okay, so okay, thank you, Subhasis again.
Thanks everybody. I am sure you had a great school, and Vedang will make sure that it continues. But please give good feedback, I think, because not that just it is okay kind of thing. Give a critical feedback so that it could be things could be changed or modified. Anyway, thank you, Siddharth. Thank Shoikat and both institute colleagues for taking this effort. Thanks a lot. Okay.
Okay, so I request everyone to not to leave the meeting because we have